Cool. So let's start. I have a lot of slides and not enough minutes. At the end, I have 2 books here to give out. So for the first 2 questions, if you have any, you will get the free book. And I also have some stickers of Halidon, so they are free to take. Thank you for coming. I will be talking about brief history of the virtual threads. It's kind of a talk which will explain how we got where we are right now. I'm Daniel Katz. I'm a Halidon developer from Oracle. You can find me on various social networks and ask me anything over the DMs after that. The agenda is, of course, the virtual threads. We will do really small intro into it. I will, instead of explaining what is it, you probably all know something about the virtual threads. Everyone has saw some talk about it, right, with million arrows everywhere and stuff like that. So I will just show some optimizations and how does it do the way it's so fast and stuff like that. Then we will move to the timeline of the concurrency in Java. So we will see some broader context of how we get where we are right now. Then we will do some time travel into the 1997, and we will take a look at the green threads. After that, we will compare it with operating system threads abstraction, which we had for so long. We will take a look at the reactive Java, and then there will be a shameless plug about the Halidon 4. I will explain how we have leveraged the virtual threads in our own web server. And at the end, if there is a time, enough minutes, we will take a look at the Achilles heel of virtual threads at the pinning. So the virtual threads, the blocking is cool again. And finally, with virtual threads, we have delimited continuations in Java. You can now choose if you want to create a virtual thread or the virtual user thread or the physical thread by using the very same API you are used to, because it's all nicely placed together. It is way cheaper. You can create millions of them. No pooling is needed, or it should be even like forbidden. And blocking is completely fine. The naive imperative coding style is safe again, with performance comparable to the reactive constructs. Work scheduling is done by the JVM. And we are avoiding the expensive context switching on the operating system level scheduling, saving all that of heap memory allocated for physical threads and so on. So how does it work? Well, we will jump directly into the thread class. If you take a look at how the sleep instruction looks right now, you will notice there is a if statement there, which is just checking if you are running on the virtual thread. And if you are running on the virtual thread, we are sleeping differently. If you go a little deeper inside that, you will figure out that there is a method somewhere in the virtual thread class, which is called yield continuation. And that's what it is. We are just yielding our continuation. The user thread is a continuation, and we are yielding it, so it will be offloaded from the carrier thread, and it can execute some other virtual thread, one of those millions. I won't show you those diagrams with millions of arrows. You already saw it somewhere, probably on some bazillion diagrams somewhere else. The virtual threads are scheduled over a bunch of physical carrier threads. You can see it in your own IDE. This is from my IntelliJ idea. You can see it's a for-join pool. It's actual scheduler for the user threads on top of the carrier threads. So what you see is actually those for-join pools carrier threads running. The scheduler. The for-join pool as a scheduler is actually a marvelous and battle-proven piece of engineering we have in Java for quite some time now. We'll get to it later, and it's what happens when we are mounting and unmounting. So what happens with the virtual thread? We are mounting and unmounting it from the carrier thread. We call this process freezing and thawing. What happens with the stack is that when the continuation is unmounted, the continuation part of the stack is actually being saved somewhere for later. I will have a really nice animation for that just on the next slide. We call this process freezing. When continuation is mounted back on the carrier thread, its stack is being copied back on top of the physical thread stack, and we call this process thawing. So there comes my nice example. We can try to demonstrate this stack manipulation with this small server example. I have created a really small server which is reading socket and is blocking there, obviously in endless loop as it used to be done. The continuation part of the stack is freezed when we run into the blocking part of the read socket. So I will try my animation right now. And you can see that the stack has moved somewhere for later usage. Our carrier threads are now free to execute some other virtual thread. When your continuation gets mounted again, it's not the whole stack that is being copied, because that would be still quite expensive. We want to be really fast, right? So instead of copying the whole stack back on the carrier thread, we will move just small part of it with a special frame which is called return barrier. It's a lazy frame which will load the rest of the stack when it's needed. And this is a very cool optimization, because when we are running in this endless loop, like in this example, we actually don't need the whole part of the virtual thread stack. We need only this. Most of the time, we will need only the part which is rotating inside that endless loop. So when we are getting back, we will hit the return barrier, and we will load another frames like that. So now, still part of the virtual thread stack is being saved for later. It's even if it's being unused for some time, it gets compressed. There is some other optimization which is running on garbage collector thread, and it's compressed the stuff so we don't use so much memory. It has some really cool optimizations there. But the main message here is that we don't really move around the stack that much in the end. We are again hitting the yield continuation, and that's all my nice animation demo. If you want to go more, there's really great talk about this from Ron Pressler. It's on YouTube. It's from the last year's JVM Language Summit. It's called Continuations Under the Covers, and he explains this way better than I do. I have a better animation though. Now let's go to the bit of Java history. We will put the Java concurrency in events on a nice timeline, so we can see the context a little better. So as you can see here, this is somehow the milestones I consider important put together. We can see almost the 30 years of Java in here. And I don't see color really good, but at the top you can see the ribbon in which you can see which parts are when we have the virtual threads, which parts are when we have the green threads. We will get to the green threads shortly. And there is a really long part when we have been using physical thread abstraction. At the start, we had the green threads in Java. That was actually also a user threads. There is some difference, we will get to it, but we had to get rid of them. We'll also get to the reason why that happened. In 2000 in Java 1.3, the green threads has been dropped and we switched to the physical thread abstraction. But by that, we have been leaving the scheduling of the threads on top of the CPU to the operating system, which can be quite expensive. Not everyone was okay with that. There was Doug Lee already proposing a new joint framework for scheduling the threads in JVM itself. The paper was from Doug Lee over there. He was not alone. 7 years later, there was several other papers. You can see really cool names there. There's continuations. There was a paper about continuations in the Java in 2007. In 2008, there was another one that's from that was actually a functioning library from Matthias Mann. There was first implementation of the continuations in Java. It was made for some game development in Java. It's kind of interesting because you needed to be fast and not so complicated. After that, there was another paper. You can see those cool names, Lukas Stadler and Thomas Wettinger. If you are following the development of the GraalVM, you will figure out that those guys are actually the ones who are behind all the cool stuff there. In 2011, in JDK 7, that was the last one which was codenamed. It had codename Dolphin. We got the actual implementation of the for-join pool, and it came from the Doug Lee. So thank you, Doug Lee. You have invented it, you have implemented it for us, and we had it in Java for quite some time. They didn't end, you know. In 2012, the Go 1.0 is released with Go routines inspired by Erlang, and proves that delimited continuations are really cool. And in 2013, Ron Pressler releases his first version of Quasar library. That was a library for using lightweight threads inspired by Erlang and Go and Matthias Mann's library. So we again had a kind of continuations in Java. In 2014, the RX Java comes out, the 1.0. And that's, you can consider as a peak of the reactive programming. Java is getting really reactive. Everyone needs to do reactive coding because it's super fast, it's super great, and it's super nice, right? After that, the Kotlins comes out with coroutines. Again, they are attempting to do continuations Java to schedule the work inside the JDK. But in the same year, the Ron Pressler is drafted to Oracle to work on adding continuations and fibers to JVM. That was how it was called at that time. He joins the Alan Bateman and all the other guys on the Project Loom, and it gets into the motion. And from there, it's actually getting pretty fast. We get the first preview in JDK 19 in 2022, and in 2023, we got with Java 21, we got the virtual threads, which we can finally use. And they are super fast. They fit together nicely with the existing thread APIs, and everything is great. And as a scheduler, we are using the Doug Lee's for-join pool, which is a really nice piece of software, battle-proven in Java for several years already. And now we can do a little recap. What are the virtual threads? The user threads in Java, they are scheduled by the for-join pool. They are inspired by Erlang, Go, and Quasar. It's a many-to-many model. We have many carrier threads running many virtual threads on top. And what's the difference between the user threads we already had, the green threads? We will get to it shortly. For that, we have to do a little time travel. We will time travel into the 1997. Why 1997? Because it was pretty cool year. The Bruce Willis still has hair, right? The Max Verstappen is born. And Sun CEO Scott McNealy is on the cover of the Fortune magazine dressed as a Java man. So it's pretty cool year for Java. And also in 1997 was already out Java 1.1, which is the earliest and easiest JDK you can try the green threads on right now. Where I found it is we in Oracle has this archive for the JDK, so you can find really old ones there. So you can download the one for the Solaris, which supports the green threads. You also need a Solaris for that, so that's what I did for you, so we can try it out. First thing you notice about this really ancient JDK, right, from the 1997, is that the Java executable in the bin folder is, in fact, is not a binary. It's a Korn shell script which gets together the right bits of the JVM based on the architecture, selected threading model, and so on. You can see that there are two options, the green and the native threads. There, the green threads are the default. Before we move ahead, we will take a look at the Wikipedia, what the green threads are. It's explained there in a similar manner. But the important thing, important part of this explanation is that it emulates multi-threaded environment. And that's the main difference between the green threads and between the virtual threads. The green threads were only emulating it. It was multiplexing over single thread, nothing more. We can try it out. Again, we will compare it. The green threads are many-to-one model. We are running always on a single thread. Back then, it made a lot of sense because there wasn't that much of the multi-core machines, right? So, so running on the single thread wasn't such a bad idea. There was already a Solaris threads library that was also many-to-many model. It was one level lower. We'll get to it in one of the diagrams later. That was the same model like the virtual threads are using, but not in the JDK itself. And one-to-one model is the OS thread abstraction we have been stuck with for over 20 years, right? So we will try it out. We will create this really simple example when we will start 3 green threads. We will let them sleep for a while and check if they are, you know, running in parallel, how well they will emulating this parallelism. As you can see, I have compared with those nice switches. I could have compared how the native threads are running against the green threads. You can see it looks pretty much parallel. We are starting 1 and 2nd and 3rd thread, and we didn't stop anything yet. So it's probably overlapping. Now let's make it a little harder. This time, no sleeping. We are going to abstract the thread with some actual work to pin it, you know, so no one else can use the one multiplex thread. The virtual threads would be quite okay. I have like 20 cores in this computer, so it would be okay. But the green threads should have a problem. Someone could say here, okay, but you know the for loop will be unrolled. But we are in the Java 1.1. It won't. It will be really pinned. So this time, situation is quite different. The emulation is not good enough. You can see on the first one, we are running the native thread. Again, everything is nicely parallel. On the second one, we are running the green threads, and you can see that is not parallel at all. It's actually starting and ending the threads one by one, so it's actually being serialized, and you can see that there is no parallelism whatsoever. So on the multi-core machine, this is very inefficient approach. So we had the user threads in Java. It just wasn't ready for multi-core machine. You can see again, this is the many-to-one model. This is very nice diagram from the Solaris developer guide. So we can see how it worked when we are actually mapping it to the user threads. And why we have got rid of the green threads, the actual reason is again in the Solaris developer guide. You can find the exact sentence there, to substantially increase application performance. That's the reason why we don't have green threads anymore. That's what happened in the year 2000. I have the rest of the diagrams because they are really nice. So we can see the one-to-one model, that's the one we have been using for 20 years. And many-to-many one with Solaris threads library. That was pretty cool. It was eventually replaced by pthreads anyway. But it was different from the virtual threads in a way that it happened on different level. It was a native library running behind the JDK itself. And you could have used it even without the JDK. And what's left of the green threads, this is pretty interesting because there were some code still related to the green threads. It's been recently removed by Alan Bateman when he was, adding the new features for the virtual threads. But one thing is still there. There is this flag green. So you can run your Java 23 with a green flag. It will just say that green threads are not supported anymore, like for 24 years or so. So we are back to the kernel threads. We are stuck with them for a pretty long time, and it's okay from the user perspective, kind of, because the JVM spec doesn't actually state how the Java thread should be mapped to the operating system thread. So the change is pretty okay until the year 2023, when it will be okay to switch to the virtual threads, right? It's one-to-one model. We already know that. And what are the problems? The starting of the kernel thread is very expensive. You need megabytes of memory for every kernel thread. The context switching is very expensive, and it gets more expensive the more threads you are starting. So it gets worse. It's really really ugly thing. So what we have been doing about it, we have been pooling the threads to avoid starting too many of them. We have been avoiding blocking of the thread to minimize the context switches. We have been doing that by keeping rather the small amount of threads really really busy, by organizing the tasks for them in a such way no blocking is needed. So we have been actually doing the scheduling in the JDK because we didn't have a scheduler, right? So how have been we doing that? We have been using reactive programming to make some order in it to avoid the blocking and the context switches. The code needs to be asynchronous. Don't let your thread wait for something. Continue to work on something else. Response and or result will come by callback on someone else's thread. That means that instead of blocking, we just provide some callback function which will be executed on someone else's thread, and it gets really ugly. But by ditching the blocking, we have lost natural back pressure. We can't control how much data comes back on those callbacks on different threads, right? As the callbacks are executed on the different threads, no one is waiting on anything. The order of execution is, there is no order of execution, right? And all those race conditions in your code are just waiting to happen. But luckily, we have a reactive streams operators for callback orchestration, so it got a little better. It's reactive streams API. It's a set of APIs for orchestration of callbacks, obviously, with some back pressure mechanism added. It's an attempt to bring order into the callback hell by a set of very, very strict rules. And it's even part of the JDK since Java 9. You can find it in Java util concurrent package in flow class. But while those interfaces seems to be fairly simple, the specification rules are ridiculously complicated. They are so complicated that when you try to implement it yourself, your IDE will probably warn you off that it's very dangerous, you shouldn't do that. This is from my IntelliJ, actually. Instead, there are existing libraries providing reactive primitives with operators implementing reactive streams in the builder-like patterns, usually. So there is Eric's Java from David Carnock and few Netflix guys. There is Reactor from Spring, from Oleg Dokuka, and other guys. There are Akka streams, the service talk from Apple. We have our own operators in Helidon that have been actually contributed by David Carnock. And the Red Hat guys are having the Mutiny in Quarkus. That's quite interesting implementation. They have very interesting context-aware builder pattern, if I can say it like that. That's also very nice. So there are implementations there, but still, it's a trap. The reactive programming has really steep learning curve. It's a maintenance nightmare. If you look at your code after 2 months, you are completely lost. Debugging is really hard. The stack traces are practically useless. And blocking or abstracting codes needs to be offloaded to extra threads anyway. Otherwise, terrible things are bound to happen. And reactive APIs are viral. Once you use them, you have to propagate them further to avoid blocking. To get the performance, you have to, infect all your APIs with the reactive ones. Now it's time for the shameless plug. We will take a look at the Helidon. We will do very short introduction, and then we will take a look how we use the virtual threads in it. So what's a Helidon? It's a microservice framework. Our main competitor is a Spring Boot, so that explains what it is. It's a web server built to play nice with Kubernetes. It's fully open source. You can find all the source code on GitHub. Even though we are backed by the Oracle, it's all free. And unlike Spring Boot, Helidon keeps the number of third parties as low as possible. This is because we are targeting the corporate users, and get the approval for another third-party library in the corporate environment can be quite tricky. So you don't need half of the universe for running the Hello World with Helidon. We have two flavors. We have Helidon SE and Helidon MP. Helidon SE is a micro framework. There is no magic, no injection. It's pure performance with builders and lambdas. You have to wire everything yourself, but you can, play with the switches. Some people like that more. With Helidon MP, you get annotation-driven runtime. It implements microprofile. You get JAX-RS, CDI. It's very easy to use. It's more, for our business users. Here is the comparison. You can see Helidon SE. There is a handler for GET request on the greet endpoint resource, which returns the hello world. On the other side, you can see Helidon MP. It's normal JAX-RS resource, so you can run this resource in Helidon. You can run it in WebLogic. You can run it in Payara, and it will work. This is what we changed in Helidon 4. We have ditched the Netty. We have built our Helidon on top of the Netty. Our web server was built on top of it. It was reactive. The Helidon SE was reactive, and Helidon MP was imperative because it was always, we have been offloading to the physical threads all the time. In Helidon 4, we have created our own web server from the sockets up. Everything is new. It's fully optimized for the virtual threads because lot of things changes. If you have been on the talk about Jetty, you know that the contention is very different and you have to optimize everything very differently for the virtual threads. In Helidon, you can't even turn it off. You can turn off the virtual threads because otherwise it wouldn't even work. So if you want to use a physical thread, you have to actually start a new one. Here's the comparison. You can see Helidon 3 SE, the reactive one, and Helidon 4 imperative one. You can see reactive operators right here. If you will be debugging this, this is the HTTP client. So you actually are calling some other service with reactive client. You have a lot of callbacks here, and if you will be debugging this, you will be jumping there and back, you know, through all those lambdas, and it will be in different order. It's hard to debug, hard to explain to someone how to remember how it works. With Helidon 4, everything is imperative. When you are debugging this, you are actually going from up to down. So if you are waiting for the response from the other server, you will be just, you know, standing on that request method until the response comes. So there is no asynchronicity. Everything goes from up to down. It's very easy to explain to your the new junior developer in your company, unlike with the reactive stuff. Again, timeline. I like timelines. This is how it was with Helidon. In Helidon 3, we have Jakartified everything in Helidon MP, and we have also prepared the APIs in Helidon SE to be easily switched to the imperative ones. So as you can see, the Helidon 4 came out very shortly after the Java 21 release with a new virtual thread-based web server. That is gone, and virtual threads are used in thread per request basis. Why we are fundamentally different? Well, our web server is built and tuned specifically for the virtual threads. You can't turn it off. It's not possible. It works with sockets. The work with the sockets is specifically tuned for the virtual threads. We have worked on that with close collaboration with Loom developers. Other frameworks are doing some offloading, so they are keeping the reactive server, then offloading to the virtual threads, so you can block, but you still have like both approaches. That's kind of like, you know, doing two things at once, or just retrofitting the existing worker pools. That's not that effective because again the contention changes and all the optimizations are going to work differently. Not like in the Jetty, they done it actually very nicely. And this is the comparison, you know, with reactive framework offloading to the virtual threads. You can see you have the extra abstraction layer when you are offloading to the virtual threads. With Helidon, you go straight to the, you know, nirvana of the imperative coding. It's easy to use, and you can block everywhere. And now we still have time. That's awesome. I've been really fast. Sorry if I've been too fast. We have time to take a look at the pinning. Who here has heard about pinning? Oh, awesome. This is great audience. So there is a pinning issue with virtual threads. Everyone knows that. We will take a look at it, what it is. So I actually draw this one. This is how it looks. What happens is that when your carrier threads is actually blocked somewhere, when it cannot be yielded, the carrier threads cannot be used for the next virtual thread waiting to be executed because it's being blocked somewhere. That typically happens with the synchronized block. We will get to that. Or if you get into the JNI, through the JNI interface and somewhere in your CLang code, there will be a mutex lock, and it will lock the control of that physical thread, so it cannot be used for anything else until it's released. So usual suspect is synchronized. It's not always harmful if it's really short-term blocking. By default, the 20 milliseconds is considered as a short-term blocking. So, for example, if you are using concurrent hash map, there is synchronized inside, but it's usually not a problem because you are using it for very quick logic. Short-lived in-memory operations are not harmful. In case of pinning, the carrier thread pool compensates by spinning additional carrier threads, so it doesn't stop working. It will be just, the performance will degrade because it will have to stop new carrier threads, and we are back to the physical threads and how expensive they are. Reentrant locks don't cause the pinning. They are completely safe. They are virtual threads friendly. I have prepared a small example. It's an older one. I run it on the JDK21, I think. Here we will do simple sleep inside the synchronized block, and obviously we won't get with the next thread. We won't get to the sleep, so the yield doesn't happen, and we will be blocking the carrier thread. We have two options how to detect the pinning. That's the first thing. You have to know what happened, right? So to detect the pinning, we have two options in Java. We can use the JDK trace pin thread system property. You probably read about this in many blog articles around the virtual thread already. It's very easy to use. It prints the problematic frame. You get even the line number. It's really cool. The only problem with it, we don't recommend it for usage with Helidon, because we even had some users who run it in production when they had some issue. The problem with this is that printing to system out in Java is actually synchronized. So the contention on that thing can be quite problematic. And there was, I think it's already fixed in some latest release of JDK, but in JDK 21, the deadlock was so serious that even the JCMD tool couldn't connect to the running JDK because that spinning loop was blocked too. It was just very, I haven't seen the deadlock like that in Java before. So instead of that, there is much better way how to detect pinning, and that's the Java flight recorder event, the JDK virtual thread pinned event. It's very easy to use. It's enabled by default. The default you can even specify the length after which you consider blocking to be a pinning. The default is 20 milliseconds. We already said that. You get very same result. Here you can see that you get the line, you get the frame, so you can see the stack and where the pinning crime is being committed. And the fixing of the pinning issue, the ultimate solution is offloading to the physical thread. Again, but there is the cost of performance in that. But there are cases when you just don't have any choice. There are libraries which nobody will make virtual thread friendly. There are some JNI calls into some native code. There are mutexes inside and stuff like that. So sometimes there is no other way. There is some CPU intensive task. You are mining bitcoins in your Java application, for example. So that's actually a good use case for the physical thread, not for the virtual thread ones, for the virtual thread. So that's where you do the offloading. Or you can avoid synchronize. You can rewrite your code to use the reentrant lock. Offloading in Helidon MP is really easy. You can use annotations. We have several annotations for that. You can use the manage async from the Jersey. It's actually not the Helidon one. It works only on the JAX-RS resources, but a lot of people already knows that. You just add one annotation and you are running on a physical thread from a new thread pool managed by Jersey. We have also our own Helidon annotation. It's called execute on. You can choose if you want to execute on virtual thread or on physical thread. You can configure with microprofile configuration if you want to how the thread pool should look like and so on. So that's very powerful feature, and you can offload very easily. It works even on the CDI beans. So this is very nice and easy in Helidon MP. In Helidon SE, as you are hacking your way through, because there is no magic. Indeed, you want to be really fast. You have to offload yourself. You have to create your own thread pool. In Helidon SE, it's better to use our thread pool supplier. It's a wrapper which will make possible the context propagation in Helidon SE. So, but you can use your own thread pool. It just won't propagate the context about security stuff and things like that. The nice thing about that, if you would be in the reactive runtime in the handler, you would have to use a callback. But here, because we are on the virtual thread, you can actually wait for the physical thread to finish just by blocking. So it's really easy to offload to the physical thread, even in the Helidon SE. It's not really optimistic so far. I've only told you how to offload to the physical thread again, right? So what's the future of the synchronized? Do they really mean it like that we will have to, live with the problem of the synchronized causing the pinning? The future is actually way brighter. The frameworks and libraries are replacing synchronized already. If you take a look around all new releases, the MySQL driver 9.0, which came out this summer, is already virtual thread friendly. They have removed all the synchronized. The MongoDB clients are the Oracle driver is also the virtual thread friendly. So it's getting better and better. And also a lot of synchronized usages are being eliminated in runtime. So it's not always the problem. It's not always causing the ugly pinning. And most importantly, the pinning class synchronized is really close. You can actually access the JDK prototype. You can download the early access version of the Loom build. This one is a little older. There's already a newer one, but this one has a nice release note which says that the synchronized method has been already fixed. They have also a problem with the object weight, which has been fixed in the latest early access build. So they already have the solution. It wasn't easy. They did it. And it should be JDK 25, I think. So it's really, really close. And we can try it out. I did this. I tried our example with this early access build of the JDK, and as you can see, there is no pinning being detected anymore because it's not there. The synchronized is virtual thread friendly already. So remember, in comparison with accidental blocking, in reactive code, the pinning in virtual thread doesn't look that bad. It's when you block in the reactive code, you will actually, block someone's even loop, and it will get really, really ugly. With virtual threads, you will get some performance points. You will get disqualified in that, but that's all. And that's all from me. If you want to know more about Helidon, we have the Twitter. We have really nice pages. We are writing some articles on Medium. We are completely open source. You can find all the source codes on GitHub. We are even doing some YouTubing, and we are giving some free advices on our public Slack channel. So if you are using Helidon and need some help, we will help you there. And I have the 2 books here. So any questions? Will be first. First question. I said comparable for a very good reason, because in theory, you should always be able to write a faster code reactively. But how many developers in your company is so good with reactive coding that they can actually be that good? And if they leave, will you find someone else who will be able to maintain it? So this is actually, you are hiding the complexity. It's the same trick to avoid the context switching, but you are hiding the complexity behind the scenes. So you get very close to that performance without such complicated code. Again, it depends on the implementation. We have been measuring our performance, and we got we got really close to other frameworks which are running the netty, and I think it's good enough for the simplicity of our code base. It's everything is way more simple right now. It's always better to avoid the reactive APIs. We can all agree them. The more professional reactive developers there are in Java, they more agree about that. But there are use cases where the reactive streams are uh, very good, like for the messaging, asynchronous communication. That's where it actually shines, because you can regulate the regulate the back pressure and stuff like that, and that's in the imperative approach can be more complicated actually to do. So there it can be. I really like the reactive messaging in microprofile. Only problem is it's always, again, the learning curve is very steep, so it's hard to explain it to anyone. But the use case is there. I would say the asynchronous communication over the network and stuff like that. Then the reactive streams are quite cool. But again, you want to avoid that. In your business code, you want to have as simple as possible. So after a year, when you open your code base because you are looking for some bug or something, you won't spend several nights to figuring out how it works and so on. So you two have won the book. That's awesome. It's about Helidon 3, by the way. So you can read about the reactive stuff. I wrote those. Can I walk? I will. Oh, this is. I wrote those chapters, so you can read about reactive operators we have. There is nothing about the virtual threads. I'm sorry about that. We will have to release a new version of the book. I also have some stickers if everyone wants. And that's about it. Next question. It's a good question. They have really nice API internally, but they didn't open it up. I have asked that question Ron Pressler, and he also didn't give me any definitive answers. So sorry. Yeah, I will also like that. That's a lot of people are asking about that. What is now looking like an option that that it seems like there are some activities towards the pluggable scheduler. So the for-join pool won't be the only scheduler. There can be use cases when different scheduler could be, more practical. I know the Red Hat guys have been very keen to get in their own scheduler. I'm always saying, okay, it's very tricky to say I can do a better scheduler than Doug Lee, but yeah, that's kind of cool. And maybe with that, more APIs will open up for some other tricks. The continuation API is really nice. It would be cool to have something like they have in Go, right, and so on. But this is way better than we had for the last 20 years. It's finally we have a way how to be performant and don't do really ugly stuff asynchronously. So I've got only stickers. Sorry. Thank you.